Hello, welcome to our first video on optimization. We're going to do 3 videos on this subject. Optimization is the process of finding where functions take on maximum or minimum values. We'll look at 3 problems. The first one, we'll look at the maximum area for a rectangle under a parabola. We'll then move on to some more moderately difficult problem, and then finally a very challenging problem at the end, that of carrying a pipe down a hall and around a corner. Optimization problems are usually word problems, so they involve converting your reading into symbols, pictures, and mathematics. This is often a challenging endeavor for some students. One of the ways to help you through this step, though, is realize the importance of reading. You're going to have to read and reread these problems as many times as necessary to gain understanding about what the problem's about and help you move from the words to pictures and equations. This reading is the first step in the table on page 263 of your textbook that lays out 5 steps for solving applied optimization problems. So first, as we already mentioned, is read the problem. Okay, you have to read the problem again and again until you understand it, know what is given, what is the unknown quantity to be optimized, etc. Now, next you want to draw a picture. Label anything that might be important. If you're trying to find a volume, what are the dimensions you need? If you're trying to look at an angle, what might you use to represent the angle? Introduce variables. Okay, list every relation of the picture and the problem as an equation or algebraic expression, and then identify the unknown variable or variables. Fourth step, once you've got a good picture, decided what's important, put variable names on it, you want to try to write an equation for the unknown quantity, that is the thing you're trying to maximize or minimize, and express it hopefully as a function of a single variable involving some of the things you've labeled in the picture. Now sometimes this won't be possible, at least not immediately. You may have to use 2 equations in some cases and use one of the equations, known as a constraint, to eliminate one of the variables in the other equation. Once you're at this point, you're back really in a section 4.1 problem where you have a function of one variable and you're asked to find the max and minimum. So we'll then move on to finding critical points, looking at endpoints, and deciding which of those is the point that leads to the extreme value that we seek. Now, I've added a couple more steps to this process. Number 6, once you're done, think about your solution. Does it make sense? Often this is something like, hey, I'm finding a volume. I got a negative answer. Wait, that can't be right. So go back and find out what went wrong. And then make sure you read the problem again, see what's being asked, and state an answer in complete sentences. Make sure you've answered all the questions asked, provided all the information asked for. So let's see how this works in a simple problem. So we're going to imagine a rectangle that has one side on the x-axis and the other 2 vertices are in the upper half plane and lie on the parabola with equation y equals 9 minus x squared. Let's find the maximum possible area for a rectangle of this sort and describe the position and say other features about the rectangle. So read the problem again and then pause the video and see if you can't draw a picture to go along with this problem. Okay, here's the picture I came up with. The parabola y equals 9 minus x squared, pretty obvious that you want to draw that. And then here is a possible picture of a rectangle with one side on the x-axis as described and the other 2 vertices up here on the parabola. Now what makes this problem challenging, or not obvious at least, is there are lots of rectangles one could draw. I could have a long skinny rectangle looking something like this. Don't know what the area of that one is. I could have a taller rectangle that isn't very wide, something like this. So infinitely many possibilities there. Which of those has the largest area? So we next start by labeling some important features in the problem. So the area of a rectangle is the length times the height. So we need to work with these 2 quantities. And so we've labeled them in the picture L being the horizontal length, and h is the height. So the area is given by A equals L times h. We'll use area, represent area by A. So the height, h, is the y-coordinate to the parabola above the lower right corner. So the height h is represented by this. So here's how the parabola comes into play. And so it makes sense perhaps to think about what is this x-coordinate down here at the lower right corner. So we're going to let x denote that coordinate, and then if we know that coordinate, we can then find the y height by just computing 9 minus x squared. So we've now labeled x. That's the coordinate of the lower right corner of the rectangle. And we see that if we know this, we really know all about the rectangle. First of all, let's look at the length. So the x is going to be positive. The lower right corner can be anywhere between the origin out here to the point 3. Again, we saw illustrations of that on the previous slide. The length runs from x to minus x there. So the length of the rectangle is given by 2x. So we're going to use 2x instead of L for the length now. We're going to try to find the x that gives us the rectangle of maximum area. And again, once you know x, where this corner is, this lower right corner, we can figure out the height h. It's just the height to the parabola. And so the h then is given by 9 minus x squared. So area, which was L times h, is now given by 2x times 9 minus x squared. Furthermore, if we do focus on the location of this lower right-hand corner here, then we know the x has to be between 0 and 3, so this gives us an interval on which we seek our variable. So this is nice because back in 4.1 we learned how to find maximum and minima of continuous functions defined on intervals like this, where you have a finite interval and endpoints. So in this process, reading the problem, drawing the picture, labeling the variables, and then finally expressing the thing we want to minimize or maximize, the A, in terms of these variables, we've reduced the problem from a word problem to one involving just maximizing or minimizing a function. Okay. So, move on. Our problem now, we've reduced it to finding the maximum value of A. We'll still use A for area. That's 2x times 9 minus x squared. We can expand that to get 18x minus 2x cubed, and we're only interested in x's between 0 and 3. So going back to 4.1, we want to find the critical points for this expression on this interval. And because this is a polynomial, it's differentiable at every point, so the only critical points are the x values in the interval 0 to 3 for which dA dx equals 0. So, as we have done many times in the past, we take the derivative and set it equal to 0. So the derivative of 18x minus 2x cubed, we stop here, is just given by 18 minus 6x squared. And setting that equal to 0, pretty easy to solve. We find x equals plus or minus the square root of 3. Now remember, again, we're looking for x's in the interval from 0 to 3. So because of this, we are going to ignore the negative solution and just focus on the critical point x equals root 3. So at this point, as we learned in section 4.1, we know the maximum for A occurs at one of the critical points, and we only have one we're concerned with, root 3, or at one of the endpoints. So we now have some candidates for where the maximum occurs, and we can find out which of those corresponds to the maximum just by computing the area for each of these 3 examples. So first of all, we'll take the easy one. What if x equals 0? That computation is done here. We just put 0 into the area equation. And of course, pretty obvious that's going to turn out to be 0. In fact, if we look at the situation here, here is that parabola. And if x equals 0, that means that our lower right corner is right here at the y-axis. And our rectangle is a very tall, thin, in fact, it's just a tall, thin line, which has area 0. The other kind of silly one is the other endpoint, x equals 3. That corresponds to taking the lower right corner of the rectangle down here at the point where the parabola meets the axis. That's the point 3. And that rectangle will not have any height, and so it too will have area 0. Now, sometimes it'll seem kind of silly to check the endpoints because they give obvious zeros like this case, or they may think it's clear that the max or min cannot be at the endpoints. Nonetheless, get in the habit of checking them in every case because we will look at problems where the max or min does occur at an endpoint. Finally, the third possible point is the critical point, x equals root 3. If we take root 3 and put it into the area equation, we have 18 root 3 minus 2 times square root of 3 cubed, and the algebra from that gives us 12 root 3. And since that number is clearly bigger than 0, which we found for the other two cases, we know 12 root 3 is the maximum possible area. So we're going to tell people that we think the maximum possible area is 12 root 3. Does this seem reasonable? Well, yeah, it's a positive number. Area should be positive. And I just think it seems plausible, so we'll go with that. We can also designate the vertices here. The x equals root 3, remember, told us the position of the lower right vertex. So there's one of the vertices on the x-axis. The other one is symmetric on the other side. And then the y height, if we compute the height, the y height, by looking at 9 minus x squared, as we saw earlier, we get the y coordinates for the points above the axis points. And so those are the 4 vertices of the rectangle. So in summary, here's what we found. The area of the rectangle of maximal area has area 12 root 3, and it would look something like this as it is inscribed under this parabola. It has a length of 2 root 3, and the height turns out to be 6. So you might study this. Make sure you can work through problems of this nature, of this simplicity on your own. And when you're ready, move on to the next video to look at a more challenging problem. We'll see you in the next video.